All right, welcome back to this lecture of Nature and Code. So we just implemented the first 5 lines of our Hardy-Weinberg principle in JavaScript. And this is what the code looks like. So we had the 3 variables defined for the genotype frequencies, and we had the 2 variables defined for the allele frequencies, and we calculated those frequencies here based on the genotype frequencies. So now what I would like to do is I would first output some data here into the console because this code is executed, but nothing is ever shown in the console. So I guess at this point, I basically want to output the genotype frequencies. And I'm going to do this again with this method console log. And I'm going to write here generation 0. And now I could do it in 2 different ways. I could either do something that is called string concatenation, where you would basically add strings together like this. I'll talk about this in a second. A1, A2, and then here another \t, and then A2, A2. So the \t is the tabular character. So this would just introduce a tab. So this whole thing here would just add all these substrings, if you will, together and create one huge string. And actually, let me add a tabular character here as well. So now if I would save that and go back to the browser and reload the page, now I would see these genotype frequencies here. So what you see here is generation 0, 0.15 for the A1A1 genotype, 0.5 for the heterozygote A1A2, and 0.35 for the homozygote A2A2. And this value here is calculated, whereas these two were hard-coded in the variable assignment. So this works. However, sometimes it's a little bit cumbersome to concatenate strings like that. Console log is actually a method that takes any number of arguments just separated by commas. So you could just say here, generation 0, and then you would like to print the string A1A2, A1A1, comma, and then the string A1A2, and then finally the string A2A2. And this would by and large do the same thing. So if I would save this here and then reload the document, it's color coded slightly differently, but it actually looks even a little nicer. So I'm going to just use this type of syntax. So just want to mention one thing here, and we're going to talk about this in detail throughout the book. But what I'm doing here is I'm using a method or a function. These are almost equivalent, and we'll understand more about the difference down the road. But this is a piece of code that is hidden somewhere or defined by you, but it's a functionality that you can just call by calling the name of the function. So in this particular case, it's called console.log. And then in parentheses here are so-called arguments, and you pass in the corresponding parameters for these arguments. So as I said, this is a method that takes multiple arguments, and in fact you can pass in as many parameters as you want to. It's a very generic function, but in general, and we'll talk more about this in the future, but in general, it's you just simply call these functions by calling their name, and then followed by these parentheses, and then whatever you want to pass on and whatever the function requires as parameters. Sometimes many functions don't take any parameters. In this case, you would just write, open and close the parentheses immediately. And sometimes you would add multiple ones, and then they would be separated by commas as they are here. Again, we'll talk about this in detail because functions are really at the core of any programming language, but I just want you to understand the structure of this line of code here. All right, So I have one other task. I would like to now to calculate the genotype frequencies in the next generation. Okay, so I'm just going to calculate the genotype frequencies in the next generation. And so that I know what I'm doing, I'm just adding a little comment here. I'm going to write genotype frequencies in next generation. And this is actually quite important. So a double slash is a comment. So anything that follows after a double slash is considered a comment and is not considered code that needs to be executed. So this can be quite powerful. Often you would like to sort of annotate your code and add a comment either for yourself or most of the time for your future self or for someone else who's just reading the code. Obviously, it's best if the code is written in a way that's self-explanatory, but sometimes that's not possible, and a little hint with a comment can be quite helpful. And you can see here my Text Wrangler text editor highlights this in a very specific way, which I quite like. All right, so I'm now just going to reassign new values for A1A1. So A1A1 is now going to be calculated based on these allele frequencies. So we know, right, that it's going to be P times P. This is what we, figured out when we developed the Hardy-Weinberg principle. Correspondingly, A1A2 is going to be 2 times P times Q, so 2PQ. Oops, times, where's my times here? Q. And A2 will be Q times Q. So about these lines, they're pretty straightforward again. Here we have multiplication. We didn't have this before, but it's straightforward. You can see that I'm not using the var keyword here anymore. That's because I have already defined those variables up here, and you only need the var keyword when you define the variable the first time. After that, you can just use the variables by just using their names. So let me now see what this would write in the next generation. So I'm just going to copy this line here, and I'm going to put it here. So again, I'm going to log into the console the values that I have at A1A1, A1A2, and A2A2, and now, of course, it's going to be generation 1. All right, so let's save that code, and let's reload the document here. And here you can see this works. So now in generation 1, we have 0.1600 and so on for the A1A1 genotype, 0.48, so a little bit of a reduction for the A1A2, and 0.36 for the A2A2. And if you go back to the earlier lectures where we calculated this mathematically, you see these are exactly the numbers that we would like to see. Obviously, there's an elephant in the room, and it's this fairly strange way of writing 0.16 here. It says 0.16 and then a bunch of zeros, and at the end, here's some sort of a rounding error. What is this, and where does it come from? Well, so unfortunately, that is something we have to deal with, thankfully, quite rarely, but we have to keep it in mind. And it's because computers fundamentally store information in a binary format with bits, which is either 0 or 1, or on or off. And excuse me, you will, if you store a number or a floating point number like this one in a computer, you will store it in a number of bits. In particular, JavaScript uses 64 bits to store floating point numbers. And given a specific system, there's just going to be some inherent limitation with respect to the precision. And I want to make an example that brings this home perhaps a little bit more clearly. Now, if I would tell you, give me 1/3 in decimal notation, okay, 1/3, 1/3. The definition of 1/3 is if I add it together 3 times, then it adds up to 1. Okay, so 1/3 plus 1/3 is obviously 1, exactly 1. Now you could tell me, okay, it's 0.33. Fine, let's see. Let's add 0.33 3 times, and we'll get 0.99, which is not 1. All right, you say, I'm going to just add up my precision. I'm just going to increase my precision here, and I'm going to say 0.3333. Fine again, let's do this. Again, this will not add up to 1. It will only add up to 0.9999, and so on. It doesn't matter how many 3's you would add here, it would not add up to 1. There would always be a little bit of imprecision. And to deal with that, you would at one point, of course, just introduce a little bit of rounding. And that's exactly what happens when you represent floating point numbers in the binary system rather than the decimal system as well. In fact, it will happen in any system. There will just be a rounding error. And that's exactly what we see here. So this is a rounding error. And it's not a big deal. It's usually a big deal if you start adding up these numbers, and then the error will be added up as well. But usually you won't have to worry about this. There will be one example later where we will have to worry about this a little bit, but by and large you don't have to worry about this. And it's usually just a sort of visual worry. This looks a little ugly, and we can deal with this later on. All right, so let's go back to the code. So I've now successfully calculated the Hardy-Weinberg genotype frequencies. I said in the beginning, though, that I would like to do this for the next 5 generations. So how should we do this? Well, there's a very easy way to do this. Basically, just copy this code here and paste it, okay? So this is generation 2, generation 3, generation 4, generation 5. And to make sure I'm actually really printing the correct thing, I'm going to change this 1 to 2 here, this 1 to 3, this 1 to 4, and this 1 to 5. Okay, so now I'm going to save this, and I'm going to reload the page over here. And indeed, we see here the Hardy-Weinberg frequencies, and we see that it doesn't change over time. Now, I hope you felt quite uneasy when you saw me copying this code. You know, the calculations are correct. Every generation, we calculate the genotype frequencies based on the allele frequencies. However, you can of course see that this is completely duplicate code, and that's really not the way we should do this. Duplicate code is generally very bad. It is bad because, well, if it does the exact same thing, why do you even have duplicate code? It's usually laziness. You say, oh, I need this code and I've already written it up here, so let me just copy it and paste it down here. Fine, it works. However, if you later need to change the code, and as a rule of thumb, you will always need to change your code for one reason or the other, then you will have to remember that you use this code in 2 locations, and you will have to go and edit it and change the code twice. And then, of course, if you have it in multiple locations, then it just becomes a maintenance nightmare. So whenever you copy code and it does the exact same thing, you're kind of doing it wrong, and you have to think about an alternative way to do this. And the alternative way is to use a function. So a function is basically a construct that allows you to encapsulate a certain logic. Like, for example, here, calculating genotype frequencies based on allele frequencies, and then encapsulate this logic into a function. And then rather than copy pasting this code, you can then just call this function over and over again. And we're definitely going to implement this in the next lecture. So see you there.